So in this video what we're going to look at is both vertical and horizontal stretching and compressing of the tangent function. So we'll dive right in here with an example. It says graph 3 periods of f of x equals 1/2 tangent of pi over 4x. And the key when we look at this is to understand that we aren't adding anything out here, so there's not going to be any vertical translation of the graph, and we're not adding anything or subtracting anything from the input variable, so there's not going to be any horizontal translation of the graph. So this is just going to be vertical compressing actually, and then a modification of horizontal stretching of the period caused by these multipliers. So the easiest way I think to graph a tangent function that's only been stretched or compressed vertically and horizontally is to understand that it's going to have the same basic shape as the tangent function does. So start off by just drawing one period. It says draw 3, but start off by drawing one period of the tangent function if you're doing a hand drawing. So just establish your vertical axis, establish your horizontal axis, and then think about what the tangent function looks like. Well, it usually has a vertical asymptote at negative pi over 2 and equally spaced on the other side of the output axis. There is another vertical asymptote at pi over 2 or 90 degrees. And this happens at pi over 2 radians. This happens at negative pi over 2 radians if we're in radian world, or negative 90 degrees and 90 degrees if we're in degree world. And we know that the tangent function passes through the origin. It contains the point 0, 0, and we know that it's asymptotic with its vertical asymptote. So it goes like this. It sweeps down through the origin, sweeps through and down along its other asymptote. So this is one period of just the tangent function, f of x equals tangent of x, and we want to treat the tangent of x like it's a toolbox function, and then think about what these transformations do to the toolbox function. So it's just a pre-calc exercise really. I probably should have left that instead of trying to make it look nicer. So the other key point that we kept track of when we introduced the toolbox function is we said halfway between the 0 and the vertical asymptote. Halfway between the 0 and the vertical asymptote we have another key point on the graph. We said when this point here, this is the ordered pair. If you input pi over 4 or 45 degrees, the output's a 1. And here, if we input negative 45 degrees or negative pi over 4 radians, so this is the point negative pi over 4, the output is negative 1. We had odd symmetry with the tangent function. So the key is that this point and this point are really excellent points for keeping track of vertical stretches or compressions, because if the tangent function equals 1, a half of 1 is just a half. If the tangent function equals negative 1, 1/2 times negative 1 is just negative 1/2. So right away, this 1/2, which is a vertical compression, so we have a vertical, maybe I'll write it right here, that we'll have a vertical compression by a factor of 1/2. We just get rid of the 1 and put a half there. 1 times 1/2 is 1/2. Negative 1 times 1/2 is negative 1/2. This is going to change the angles. This is going to change the period of the function and change the angle measure. So these are going to change, right? We'll worry about that in a minute. Those aren't going to be pi over 4 and negative pi over 4 because this multiplier on the x is going to cause a change in the period. So to get at the change in the period, what we want to remember is that the distance between vertical asymptotes is 180 degrees or pi radians. And this pi over 4 times x, this pi over 4 is going to change this. In fact, this is about 3/4, so it's going to cause a horizontal stretching. It's going to slow how quickly the graph happens down. It's going to wind up stretching it out. And what we want to do is figure out, okay, well, how does the pi over 4 impact the period? So the period is usually pi over 4. Now the question is, what value of x generates, usually the period is pi radians, so the question is, what value of x generates an output of pi radians when we have a multiplier of pi over 4 on the x? So we just come down here and figure that out. We'll say, hey, we have pi over 4 being multiplied by our input variable. What does x have to be to generate a period on the tangent function? And a period happens to be pi radians. And now we just multiply by 4 over pi on both sides, and we get x equals 4. So the adjusted period, instead of pi radians, it's going to be a 4. So the distance between vertical asymptotes is 4. So this isn't going to be a pi over 2 anymore. The distance between vertical asymptotes is a 4. And we know that we've broken this into 4 equally spaced regions. 1, 2, 3, 4. So to get the tick mark distances, I just take a fourth of the period. So I go, hey, 1/4 times 4 equals 1. Oh, the tick mark should be, the first tick mark should be 1. The second tick mark should be 2. If I'm counting the other direction, this will be -1, and this will be -2. The other way that we could have gotten it, instead of just finding the period directly, so another way of getting at this would be to say usually this vertical asymptote is at pi over 2 radians, and we could ask the question, what value of x when multiplied by pi over 4 gives us our vertical asymptote, which is at pi over 2. So we could have done pi over 4 times x. When does that equal the vertical asymptote pi over 2, and multiply both sides by 4 over pi, and we would get, at the pi's cancel, we get 4 divided by 2 is 2. We know that the tick mark here is a 2, and then we would take half of 2 to get the point halfway between the 0 and the 2. So half of 2 would be 1, and we know we have symmetry with respect, we have tick mark symmetry with respect to, or vertical asymptote symmetry with respect to the y-axis. The function doesn't have y-axis symmetry, but these spacings do. So then we would get -1, -2. It's kind of your choice how to do it. Anyways, you can take the stuff in here and set it equal to the vertical asymptote and figure out what the new vertical asymptote value is going to be based on the multiplier pi over 4. So once we do this, we are in good shape. We know this is a 1, so this will be a 1, and this will be a -1, and then it says do 3 periods. So what we're going to do is look at the spacing. We're going to eyeball it and try to give a vertical asymptote here following roughly that same spacing. And we know halfway between is the 0. We'll get tick marks halfway between those so that we have 4 equally spaced regions. And then we just redraw the tangent graph. Putting in our key points, we're counting by 1, so this will be 2, 3, 4, 5, 6 right here, and at 5 the output's still going to be the 1/2. We're getting that key point, and at 3, halfway between the 0 and the vertical asymptote, we're going to get the other key point input, 3 output, -1/2. And then we need to do it one more time. It says 3 periods, so I'm going to look at the spacing, eyeball it, give myself a vertical asymptote. Between the 2 vertical asymptotes, break it into 4 equally spaced regions. I know I passed through the 0 here. Draw in my tangent function, trying to sweep along the asymptotes as best I can, and then label in these 2 key features. This is -1, -2, -3, -4, -5. We're at -6. This is -5, -1/2. So these numbers should match all the way across. We're repeating the same pattern over and over again. At -3, the output should be 1/2, and there I've got 3 periods of that tangent function. So we'll do one more example just in case you want to see it done one more time. So here I have f of x equals 2 tan of 4x. No vertical translation, nothing being added or subtracted to the input variable, so there's no horizontal translation. So we just have vertical and horizontal stretches or compressions going on. So again, like before, if we know that we're not translating things up or down or left or right, just draw what the tangent function looks like usually, and then label things so that the labeling matches the stretching and compressing that's going on with the function. So here's my f of x axis, here's my x axis, here's all the arrows we would be expected to draw. Give myself my two vertical asymptotes equally spaced around the f of x axis, and we'll go through the same exercise that we just did. We know that usually the distance between them is 180 degrees or pi radians. We know that the tangent function sweeps along its axis through the origin and then down along, I said axis, vertical asymptote, and then down along its other vertical asymptote. And we know halfway between we get key features. Here they are, and usually it's input and angle, output -1. Usually it's input and angle 45 degrees, pi over 4 radians, output a +1. And then we can start thinking about how will these multipliers change our graph. Well, the 2 is a vertical stretch, so we have a vertical stretch by a factor of 2. So it's going to be, when the tangent function is equal to 1, we'll get 2 times 1 is 2. And when the tangent function is equal to -1, we'll get 2 times -1 is -2. So the outputs will be 2 and -2 there. So that takes care of the stretch part. And then we just need to think about how is this 4 changing the period of the graph. Usually the period is pi radians. It's not going to be pi radians anymore. So we ask the question, when does 4x equal pi? Well, that happens when x equals, we'll divide both sides by 4, when x equals pi over 4, which tells us that the distance between vertical asymptotes is pi over 4 units. And the tick marks are breaking the region between the two vertical asymptotes into 1, 2, 3, 4 equally spaced regions. So take the period and take a fourth of it. So 1/4 of the period is going to be pi over 16. So our first tick mark happens at pi over 16. Our second tick mark happens at 2 pi over 16. So we just count pi's as we move along. This will be -pi over 16, -2 pi over 16. And again, I could reduce this to simplest form, but I know I need to add in some extra periods, so it's going to be easier to count up 1 pi, 2 pi, 3 pi if I don't reduce these tick mark values. So I now have the number I need to feed in here. This is pi over 16, and this is -pi over 16, and that completes one full period. And now I can go in and draw 2 more periods. Again, we look at the distance between here and here, and we try to roughly match it within reason, not getting too ultra picky about it. We break the region between the two vertical asymptotes into 4 equally spaced regions. Halfway between the two asymptotes, we cross our 0. We draw in our function sweeping up along its vertical asymptote, and then sweeping down along its other vertical asymptote. We're going to get a key point on the graph here and a key point on the graph here, and now we can count up 1 pi over 16, 2 pi over 16, 3 pi's over 16, 4 pi's over 16, 5 pi's over 16. And the last one is 6 pi's over 16. That tells us that this point right here is going to have an input of 5 pi over 16, and the output will be the 2. And this one's going to have an input of 3 pi over 16, and the output will be the same -2 we got over here. And then that takes care of that. We come over here, let's give it one more period. So space out your last vertical asymptote, break it into 4 equally spaced regions. Halfway between is our 0. The graph sweeps down through its 0, down along its asymptote, and our key points are halfway between the 0 and the asymptotes. We get a key point here. Halfway between the 0 and the asymptote gives us a key point on the graph here. Label in our tick marks: -1 pi, -2 pi, -3 pi over 16, -4 pi over 16, -5 pi over 16, and this last one, -6 pi over 16. And if you're one of those people that just has to have them reduced, go through and reduce the fractions when you're done. Now label in your last 2 key points. So here at -3 pi over 16, the output is, we're getting outputs of 2. It needs to match these guys. The output was 2. And here when we input -5 pi over 16 for this point, we get an output of -2. And there is 3 full periods of this tangent function.